Let's talk about an invisible force, a force that builds so much of the world around us, from the salt in your kitchen to the rocks under your feet. We're diving deep into the world of ionic bonding.
Have you ever really looked at a tiny grain of salt? I mean, what's actually holding that little crystal together? It seems so simple, but it's all thanks to one of the most powerful and fundamental partnerships in all of chemistry. So, how does it work?
All right, here's our game plan. We're going to start with the atoms themselves and their big problem. Then, we'll see how they make a perfect trade, feel the incredible power of their attraction, watch them build a massive crystal fortress, and finally, we'll uncover the rules that make them behave the way they do.
So our story begins with a problem, a kind of atomic dilemma. You see, most atoms are walking around feeling a little incomplete, a little unstable, and they're all searching for a solution.
You've got to understand, every atom has one main goal in life, to be stable. And in the atomic world, stability means having a completely full outer shell of electrons. It's what the super chill noble gases have. It's the ultimate state of atomic contentment, and everyone wants in.
Now let's meet our two main players. On one side, you've got the metals. You can think of them as having a bit too much baggage. They've got 1, 2, or maybe 3 extra electrons in their outer shell that they would love to get rid of. And on the other side, the nonmetals. They are so close to being complete, they're just desperate to gain an electron or two to finish their set. You can probably see where this is headed.
And that brings us to the most exciting part of our story, a perfect deal, where everybody gets exactly what they want. It is the ultimate solution.
So, let's watch the classic story of sodium and chlorine play out. Sodium, our metal, has 1 pesky extra electron. Chlorine, our nonmetal, is just 1 electron short of a full shell. So sodium says, hey, you can have this, and it transfers its lonely outer electron right over to chlorine. And just like that, boom! The result, both of them now have a perfect, full, stable outer shell. But in doing this, they've completely changed who they are.
Check this out. By losing a negative electron, the sodium atom is now left with an overall positive charge. It's not a sodium atom anymore. It's a positive ion, what we call a cation. Meanwhile, chlorine gained that negative electron, so it becomes a negative ion, an anion. They've both found stability, but now they have a new identity and a charge.
So now we've got these 2 new particles, 1 positive and 1 negative. And what happens next is immediate. It's powerful and it forms an incredibly strong connection.
This is the ionic bond, and it's not a physical thing, like a rope. No, it's an electrostatic force. That's just a fancy way of saying it's the natural, powerful attraction between that positive sodium ion and that negative chlorine ion. It's like an invisible force field pulling them together.
You know that old saying, opposites attract? Well, it's not just some cliché about relationships, it is literally a fundamental rule of physics. And that powerful, invisible force of attraction is the ionic bond. It's the glue holding them together.
But here's where it gets really cool. This attraction doesn't just happen between 1 pair of ions. It scales up, building something huge and incredibly organized.
When you get billions and billions of these ions together, they don't just form some messy pile. They instantly snap into this perfect, repeating 3-dimensional grid. We call this a giant ionic lattice. Seriously, think of it as a microscopic crystal fortress built out of charged particles.
And the architecture of this fortress is pure genius. Every single positive ion is perfectly surrounded on all sides by negative ions. And every negative ion is completely boxed in by positive ions. This perfect pattern maximizes all the attraction and minimizes any repulsion, creating a structure that is unbelievably strong and stable. This is what gives a grain of table salt its perfect crystal shape.
So this tiny atomic blueprint has massive consequences for how these things behave in our world. Let's take a look at the rules these ionic compounds play by.
Okay, so that microscopic structure explains pretty much everything. Why do they have such high melting points? Well, because you need a massive amount of energy to break apart all those super strong ionic bonds. They can't conduct electricity when they're solid, right? That's because all the ions are locked in place. But if you melt them down or dissolve them in water, those ions are suddenly free to move around and carry an electrical current. That's exactly what an electrolyte is. And why do they shatter instead of bend? Well, if you hit a crystal just right, you can force the layers to slide.
Suddenly, you have positive ions right next to other positive ions, and negative next to negative. They repel instantly, and the whole structure just breaks apart.
So let's just recap the whole story real quick. It all starts when an electron makes the jump from a metal to a nonmetal. This creates positive and negative ions. Those ions are then powerfully attracted to each other, and this attraction builds a huge, repeating, super strong crystal structure, from a simple trade to a crystal fortress.
And that leaves us with one last really fascinating puzzle. We've just spent all this time talking about how unbelievably strong these ionic bonds are. I mean, we called it a crystal fortress. And yet, something as simple and everyday as water can come along and just tear that entire fortress apart. How is that even possible? Well, that's a story about a whole different kind of chemical interaction. For another time. Thanks for joining me on this one.